Okay, I would like to welcome everyone to attend today's colloquium. I'm truly pleased today that Professor Frans Oort from Utrecht University is giving a talk here. And there are several things I would like to first say before the talk. First, Frans, of course, is the international leader in algebraic geometry. And personally, over the many years, I have benefited a lot learning a lot about just not only mathematics, but more to the point, I think, the how to be a better person. Yeah, Frans is it also one thing I think is truly special about Frans. So Frans, I think, almost single-handedly established the Dutch school of algebraic geometry and number theory. And in the context of mathematics in Taiwan, there is certainly a lot we can learn from Frans. And today's talk, the format, is also a little different. This is an experiment, I have to say. And the reason for this was that I learned firsthand that at Utrecht, it doesn't seem to be true for other places, but at Utrecht, the system for colloquium is a little different. It's a 2 times 45 system. And the axioms is that in the first half, the first 45 minutes, the rule is that every faculty, be pure mathematicians or going through statisticians, everyone must be able to understand everything. And the faculty were not shy to enforce the rule. And then there's a 5-minute break in between. And then those who are interested for the rest will stay, and those who have other more important things to do feel free to go about their own business. So I thought it might be a good idea for us to try this once, and with a person who has first-hand experience. So today, any, let's say faculty, modeling on the Utrecht system, if any of you feel that there are anything, especially on the level of definitions and concepts that you don't know about during the first 45 minutes, feel free to ask. Frans guarantees that you will be able to understand the first 45 minutes. So I won't say anything more. Well, let's welcome.
Well, thank you very much, Julie. I'm feeling a little bit shy after this introduction. And I think the biggest responsibility is with you this afternoon, because please interrupt me as soon as there's anything which is not clear during the first part. I would like to thank the Institute of Mathematics of Academia Sinica very, very much for this invitation. I enjoy every minute of my stay here. Lots of intense discussions with a lot of people, and I really enjoy this very much. So thank you very much. Let me come immediately to the main point of my talk. I will discuss 3 conjectures in arithmetic algebraic geometry, and the 3 conjectures are, in a sense, completely different, both by different people, with different consequences, and so on one hand. On the other hand, the 3 conjectures have exactly the same feature, and I'll explain what the basic question is in very naive terms. And then in these naive terms, the questions will be exactly the same. And they have come up in various branches of algebraic geometry and number theory. And I will discuss, at the second part of my talk, one of the consequences of these conjectures. In my talk, I will spend some time explaining the ideas, and especially some of the basic concepts which I'm going to use. And I will give one or two extremely easy proofs. I also have the principle every talk in mathematics should contain a proof. So that's, I think, is important. And I'll give you examples. And I think, for me, examples are really very important. Because, well, examples guide you through the whole thing. Do you know the story about Richard Feynman? It is in his book, Surely You're Joking, Mr. Feynman. It's a beautiful description how he's visiting Japan, and at a certain moment he's in a room, and there's one Japanese explaining a very, very difficult theory, and Richard Feynman is sitting there looking at this blackboard full of equations, and all of a sudden in the middle of the explanation he asks, is this equality really correct? And this person is taken aback, and he looks at these formulas, and then he thinks, this is God himself sitting there. How can he, in the midst of all these formulas, find out that's a mistake? Because indeed, there is a mistake. The left-hand side is not equal to the right-hand side. Okay. Richard Feynman explains us his method, his technique, and in my algebra class I always insisted that students should use the technique. The technique is that you have in your head one example, and every theorem which appears on the blackboard or on the screen, you test again that example. And if the theory is not correct for that example, then it's false. So please use examples as guidelines, and I hope to give you enough examples to have guidelines on one hand and to enough examples to understand what these theories are about. So I will discuss today 3 conjectures with you, and these 3 conjectures I will abbreviate as the Manley-Mumford conjecture, and I won't write down the names because you see what it is. The second conjecture is the Underwood conjecture, and the third conjecture is the Hacker-Orbit conjecture. And these 3 conjectures, they will, so one is Manley and Mumford. Manley and Mumford are 2 mathematicians. Andre and Oort are 2 mathematicians, and Hecke is also a mathematician. And these conjectures have come up in various settings. And in order to formulate these conjectures, I need 3 concepts. And one concept is of an abelian variety, and the second is the concept of modular spaces, and the third is the concept of heuristic topology. And in my first part, in the first part of my talk, I really hope to give you examples and definitions of abelian varieties. I will tell you something about modular spaces, and I'll tell you something about heuristic topology. And these 3 basic tools I would like very much to come across to this audience. And then whether these conjectures are true or not, what the proofs of these 3 conjectures are and so on, that's something far beyond any general talk. On each of these 3 conjectures you can spend the whole semester teaching and not just 1 hour of talking. And I would say something. And at the end of my talk, it will come back. 17 years ago, Ching-Li Chai had a beautiful theorem in one of the leading journals. And at the same time, I had an idea about the same kind of problem. And that's difficult for our collaboration. Ching-Li has the beautiful theorems, and I have some vague ideas and questions. And so we started working together on one of the conjectures, the third conjecture, the Hacker-Orbit conjecture, which Ching-Li proved in one particular important case, and I had a conjecture how it should behave in general. And for these 17 years, Jiggy and I have been working together, and every time it was exciting for me. And Jiggy, I thank you very heartily for sharing all your deep insights with me and for your open mind during our many discussions. Thank you very, very much. So let me first tell you a common formulation, and apologies if this is a bit vague. So the point is, in all the three questions, in all the three conjectures, we have some variety. Variety is something given by equations, but you might think of the affine line over a field, or you might think of some projective variety or whatever. And in this variety, you have a set of points. And to attach your intuition to it, usually the variety has a geometric meaning. You can compute its fundamental group, you can do all kinds of geometric operations on it, on one hand. On the other hand, these points usually have an arithmetic and not a theoretic meaning. And if you find a point and you want to find more points, you have to enlarge your base field. So in general, we like to work over a field as small as possible, and then see what happens if you want to find more points, you have to find larger fields. So this finite set of points has an arithmetic meaning, usually, and the variety has a geometric meaning. And these conjectures, they're very similar in some sense, connect the properties of those individual points on one hand, and the geometry of that variety on the other hand. So you have a variety, we study a set of points, and I'll give you examples. And you can feel the set gamma, the set of points, as just a loose set of points. And you can feel the V as a really geometric object. And one can ask, suppose you have this set of points, that is that type gamma, you have this variety V, and the gamma is in V, and one can wonder, what is the closure of this set of points in this variety? Now, I warned you I'm a bit vague, and here certainly I'm vague, because I didn't tell you which topology, and actually I explained it in one topology and then changed to another one. So that's one of the keys of my talk. Okay, so the discussion of the closure of this V, of this gamma, will be the first thing. So here are the three objects of my consideration. One is the Mani-Mumford conjecture. And the Mani-Mumford conjecture, you take torsion, and I'll explain. You take it to be a variety, you take torsion in it, and the gamma will be a set of torsion points on the European variety. And just as a matter of memory, suppose this is an elliptic curve. Suppose you work over the rationals, then adding torsion points, you have to enlarge your field. So this is the typical way in which this works. The conjecture will take place in some characteristic, and here the characteristic will be 0. And I'll comment later on it in other characteristics. Now the third conjecture takes the moduli space, and I'll explain what it is. Actually, it also is a characteristic 0, and I take the endpoints. And the Hecke orbit conjecture, the gamma, will be a Hecke orbit of a point, and this is pure characteristic P. And now before I really discuss anything else, let me tell you the secret of everything what I'm doing. The secret is that you find subvarieties which do have dense set of torsion points in this case. in this case B is in the Bean subvariety, beta is a torsion point, then you translate this Bean subvariety over beta. And I'll show you that this set contains a dense set of torsion points. So in one direction, it's kind of easy. And what is the conjecture? The conjecture will be that if you take any set of torsion points, finite, non-finite, whatever you like, you take the closure of it, then that closure is a finite union of such subvarieties. So what's the strategy? You predict beforehand what subvarieties could be possible candidates for the closure. This is one of the candidates, and the conjecture will be that the finite union of such subvarieties is the closure of a given set of torsion points. Here I will introduce for you special subvarieties. And here I'll introduce in the second hour a subvariety which is called W psi. And the conjecture says that in the first case, any set of torsion points equal to 0, closure is a finite set of such bases. The Oort conjecture says any set of CM points of modular space of a Bean variety equal to 0, the closure is a finite set of special subvarieties, and the Oort conjecture says that any point, that point decides about some psi, I'll explain later, and the conjecture is that the closure of the Hector orbit is this W psi. So up to now, these things are really are all in the same method, and let me stress again that these conjectures, they are of course of completely different nature, but as I want to stress, the general outlook is the same. So let me first tell you an example, and a beautiful example, and that example will show up again and again and again in my talk. And just test yourself. Do you understand this example, yes or no? I'm working over the complex numbers, and I take complex space in dimension 1, and I take a tau, and this tau will have imaginary part positive, and I look at the lattice spanned by 1 and tau. So this is my real axis, and here's the number 1. Then I have my tau, and now you draw all kinds of horizontal lines. You draw lines like this, and all the intersection points are points at z tau, which is nothing but z plus 1 plus z times tau. Right? And now you take from this, you can embed this into Q of tau. So this is now my gamma. And my claim is that Q of tau inside C is dense. Now let me try to make a picture of Q of tau. You see an element in here, if you multiply it by an integer, and the integer is large enough, then it lands into here. So for example, let's take all the elements which have a 2 in the denominator. Okay, here's such point. This is 1, this is 1, this is 1. Yeah. And now if you take 4, right, you get bigger than this. So what you do, you divide 1 by any number, you divide tau by any number, and so this can be viewed as 1 over n z tau, and then union. And the claim is that this is dense. Well, this is of course completely obvious. The C you can write as r times 1 plus r times tau, and the gamma you can write as r z times 1 q times 1 plus q times tau, right? And now the problem is, if you take any point in C and you take an epsilon, a little ball of radius, that epsilon around that point, does it contain a point of gamma? And that's of course obvious. I mean, if you take the x coordinate here, the a coordinate here, less than half epsilon, if you take here the x and here the b coordinate, less than 2, then 1 over 2 times the absolute value of tau, but then you're done. So if you take, here you take the point x plus y tau, here you take the point a plus b tau, and you take a minus x less than epsilon over 2, you take b minus y less than epsilon 2 times absolute value of tau. Then of course the difference of these two isn't there is less than epsilon. And that's just because the q is dense in R. Right? And the fact that q is dense in R will show up again and again. So this is a typical example of a set where the set is just something like this, where the variety is just affine space in dimension 1. Mind, I do not consider this as an R space, but as a complex space of dimension 1, and then this is dense. And I'll show you that this example will show up 3 times in my talk, because this example will really be the guiding principle of everything what we're doing. Can I look into your eyes? Is this clear up to now? Yes? No protests? Sometimes it's very good if there's somebody asking just in a random question to stop the speaker if it's going too fast. So please do if that's the case. Okay, so I've proved for you that this is dense, and you see the easy proof. I used what I call the classical topology. The topology getting from the metric on the real numbers, the metric on the real numbers gives a metric on the complex numbers, and then you have topology defined by a subbasis, the epsilon rolls around points. Right? Now, that's something we are not very happy with. Who is we? We are the people doing algebraic geometry. Because the classical topology, of course, is very nice if you do analysis, if you do complexity, algebraic variety, and so on, so on, so on. But loses completely sense if you work, for example, over the integers during characteristic p. And actually, there is a p-adic topology, and the p-adic topology is completely different from the complex topology. Now, you may have integers, you may have numbers which p-adically are very close, and complex analytic are very far away, and the other way around. So these topologies don't work well if you work with algebraic geometry. And what we have learned the last century is that a marvelous thing is to work over complex numbers, then go to a number field, then reduce mod p, then study properties, then go back to the complex numbers, and so on, so on, so on. But to do this, you must have a topology which works in every situation which you want. So, for this case, the marvelous mathematician Oscar Zariski introduced the topology on algebraic variety. And so that's the first concept I really want to introduce to you. You take an algebraic variety, so think of just some space, affine 3 space, or projective 5 space, or whatever you like, your favorite one, over a base field. Your favorite one, the favorite one might be field of 2 elements, or the real numbers, or whatever. And that algebraic variety, you define a topology on it by writing equations in the ambient space. These equations you equate to 0, and these equations define you a finite union of algebraic subvarieties. And those are called the closed subsets. Now, look at this. For example, you have a Riemann surface, like the complex analysts say, or you have an algebraic curve, like the algebraists say. What is this risky topology on the algebraic curve? Well, the closed sets you get by equations, and equations are only a finite number of zeros. So what are the closed sets? It's the whole curve, the empty set, of course, for example, the equation 1 is 0, and then the finite number of points. Now, isn't that something which is really interesting? You would wonder. I'll give you several arguments to tell you that this is interesting. And the argument which I won't spell out is that you can introduce a lot of topology, geometry, cohomology, and so on, just using the risky topology. And if you look at the famous 1955 paper by Jean-Pierre Serre, Georges Courant, you see that where Jean-Pierre Serre got the Fields Medal for introducing the risky topology and then using sheaves in that topology really gives you a firm grip on almost everything in algebraic geometry. And I remind you, this technique doesn't say anything about the base field. The base field can be a field of 2 elements. Why not? For example. Okay, it's an easy exercise to see that this gives a topology. And I won't do that exercise for you. I mean, I suppose that everyone present here knows everything about topology and certainly now is convinced that this is a well and good definition, but I'm afraid that most of you will not be sure that this really is a good concept. So let me give you an example. In 1822, there was a famous mathematician, Jean-Victor Frans Oort-1, who wrote a book on projective geometry. But mind, projective geometry in that time was over the real numbers. And he struggled with a problem. For example, you take a circle, you intersect with a line, and you let the line move. And then in the 2 intersection points, you draw the 2 tangents. Right? That point is well determined as soon as you have the circle and the line. Now you move your line, and all of a sudden, this intersection point disappears because the points are no longer over the reals. So look at the following: you have a hyperbola, and you have a moving line rotating around a fixed point, and you do this construction. You take the 2 tangent lines and you take the intersection point. That intersection point depends on this line. And then Poncelet observes that while this line is rotating, you see that point moving, and all of a sudden, it's gone. Because there's no real intersection anymore. And after some time, the other point appears again. And so this point describes an orbit, then for some time it doesn't exist in his terminology, and after some time it appears again. And this principe de continuity principle says that this point moves on an algebraic curve, then it disappears, and then it moves on the same algebraic curve. And in the example I quoted you, that's easy because the line is just the polar line of the point of the parabola. But in more complicated situations, it's much more complicated. And Poncelet never proved his principe de continuité, but if you use Husky topology, the proof is easy. And the proof is as follows. You take the interval, which is the interval between 0 and 1 of real numbers. Yeah? So isn't that a strange object? So here's my interval, and here's my contact plane. And the claim is that this interval is a risky dense in c to the power 1. Yes, of course, c to the power 1 is an algebraic curve, a very nice curve. It's not even a curve, it is straight. And a closed set is either empty or a finite set of points or everything. Now what's this risky closure of this interval? It's not a finite set because it is not a finite set. So this risky closure is everything. And now what you do is improving the constant exponential to continuity is using this. This first point moving over an interval which is non-empty moves on a curve. Now later it moves also over a curve, but the risky closure of the first interval is the whole parameter space, and that basically is the proof. So this risky topology really gives you a lot of things. Okay, so the risky topology really is very nice. Note that if you have a variety over the complex numbers, your favorite to have two topologies. The classical topology, given by epsilon symbols, and the other one is the risky topology. And what is not difficult to see is that classically dense implies the risky dense. But here I've given you an example that the risky dense is not at all implying in general classically dense. So, in a sense, over the complex numbers, the complex topology is much stronger, it's much nicer, gives you a lot of things. And let me make one philosophical remark. A lot of people feel that if you do classical geometry and you draw an arc from A to B and you integrate and so on and so on, that's a very powerful method. And these poor people doing the characteristic P lose everything because there are no arcs, there are no classical topology and so on and so on. The opposite is true. In characteristic P, you have phenomena which are completely non-existent over the complex numbers. Now I'll show you in the Hacker orbit part of my talk, there are a lot of interesting phenomena happening in characteristic P, and you have very strong tools at your hand, the Frobenius morphism and so on, which don't exist at all in characteristic 0. And one of the most fruitful ideas of the last time is to work over the complex numbers, to work over number fields, to work over finite fields, and to profit from all the concepts. In the classical topology, you profit from the fact that you can make analytic parameterizations and so on and so on and so on. Then you go to characteristic P, and you profit from the fact that there's a Frobenius. And the Frobenius has certain properties, has eigenvalues, has a lot of impact